Let's talk about hash tables. So hash tables are good. Hash tables are a way to store key value data. So, Noah, can you tell us how the basics behind a hash table?
Okay, with access, yeah, we have the structure, we have a keys as a words or name, and the value is an index. So we can access the bucket that contain all the items we are interested in using the keys and the value. With the value are the index and the keys are the name. So the index, like it's the pages, similar to the example. So we access.
Okay, that's close, but not quite there. So you have keys. So you map keys to values. The value can be anything.
Yeah.
The value is not an index. The value can be anything. In this case, the value is phone number.
Yeah.
The one that's drawn here. But the hash function hashes up the key and produces an index. And the index is an index into the table that tells you where its value should be stored. Okay. All right, so that's the basics of a hash table. Key value pairs. The keys get hashed, gives you an index, and the value of the key is stored at the index that the hash function returns. So if the hash function returns a 14, then Sandra D's value, the value associated with Sandra D gets stored in index 14 in the bucket list. Okay, that's the basics of a hash table. All right, so now we're going to go through the operations and figure out. Oh, wait, first, Rakaya, when would you want to use a hash table?
So like Google search uses hash tables, like there are documents and like the words would be the keys and the values would be the documents. So like the documents that have the words and like hashed and searched for.
Good. Any other examples you could come up with for when a hash table would be useful?
I thought of like a phone directory, like a telephone book.
Yep. Yep, that's a good one. So you have a name and their phone number. Basically, anytime you have key value pairs, a dictionary, name, or the word in the dictionary and the
Meaning.
Meaning of the word. The problem with the hash table though is because of the hashing, you can't get the hash keys out in order, in sorted order. So they come out in random order, then you have to sort them. So if you need to sort them like for a dictionary, then you'd use a binary search tree. All right. Some people actually combine both a hash table and a binary search tree in the same data structure so that it can be both in order and get all the hashing performance. But anyway, lots of different ways you can do these. So those are some good examples of when you might use a hash table. So now I'm going to go back to Rakaya and say, how do you read a value in a hash table?
So we have the keys. And then we have the hash function. So the hash function will take the keys and give us the index. So, and with the index, we can access the values from the buckets list.
Good. And what's the complexity on that?
Constant time. Yeah.
Yes. So you do the hash function, and that's constant time. It doesn't depend on the hash function doesn't depend on how many elements are in the bucket or how many keys you have stored. If you store one key or a billion keys, it's still the same amount of time to compute the hash function. And so then we know from an earlier exercise that if we know the index, we can look up a value in a list in constant time. just by doing that math, you know, the index times the bucket size plus the start point of the buckets. Okay, so that makes the whole operation of a get constant time. All right, Noah, then if that's how you do a get, how do you then do an add? How do you insert a value into your hash table?
It's the same thing.
Suppose Sandra were not in the hash table yet. How would I insert Sandra D?
Yeah, we're spring. So, yeah, it's so if it's not an index, we add a new set.
We take the key and what do we do with it?
Take the key. We check with the hash. We take the key, send it to the hash function that it check the bucket list. If it exists, it's gonna return the key value. It returns the value existed. If not, it's gonna create a new set.
No, the hash function doesn't do any checking or creating. All the hash function does is return an index. So suppose I had Robert Gardner here and I hashed Robert Gardner. It would and it returned a 3. So then how would I put my value into the table?
When you look to the bucket,
I would just say buckets, square brackets of index 3 equals my phone number. Okay,
this is how you add.
that's how you add a new one. All you do is adding is trivial. You run through the hash table, you get the index, you just write the value of that index.
Okay.
Yeah, nothing you have to do. The bucket list, something I didn't mention about the bucket list. The bucket list is fixed size. So there's no insertion, no having to move things down and pull things up or anything. The bucket list is fixed size. So if your hash table says 3, you just write the value at 3. Done. Okay. So the complexity of that operation then is I do the hashing. Of 1, I do the hashing. I look up the location at that index. I just write the value. Okay, so it's all O of 1. Good.
That is why if there is no key, then we add it as a new set because then we would want to increase the buckets list size.
No, you actually never increase the bucket list size. The bucket size is fixed size. It never grows, never shrinks.
Oh.
In a hash table. So I don't have to add a key anywhere. I can actually implement this without the keys stored anywhere if I want. We don't usually do that, but it would be possible. So we don't store the keys. We don't have to store the keys. We just run the key through the hash function. It tells us where its value goes. We go write it there.
Okay.
Okay. No, it does not grow, does not shrink. So if it tells me index 2, then I write it index 2, period.
Okay.
So it's just very, very simple. Now you are pointing out a problem that what if Lisa Smith and John Smith both happen to hash to 3, then they would clobber each other. So that wouldn't be good. So this is called a hash collision. And so you do have to do some work to deal with hash collisions, but that's outside the scope of this exercise, is how to deal with hash collisions. Okay. But it's just fixed size. I get the index from the hash, store the value, done.
Okay.
Okay.
What if I mean I'm a little confused still. So what if it doesn't exist? I mean, what if our hash function does not return a key?
The hash function will always return an index. If you pass a key to the hash function, it will always compute a value and return it.
Okay.
So the hash function doesn't have a table of keys anywhere. It's not stored. It just computes. The hash function just takes this, scrambles it, divides it, mods it by the size of the list, returns that value. It is what it is. And so whether there's a value in there or not, the hash function doesn't know. It knows nothing about that. All the hash function does is takes the input, outputs an index.
Okay.
And so if I try to insert Robert in here and I get a 15th and 15th's not in there. So I just go and I write it right there. So now it is.
Okay.
Okay, so it's kind of strange in that way. There's no inserting, removing anything. I get the index, I just write the value right there. I got the value stored.
Okay.
Okay.
So can I just ask a question? Just
Uh-huh.
to clarify the key, so the bucket contained the key value.
In this example, the bucket contains only the value.
Because we have a 0, 1, and we have a,
In this example, the bucket contains only the value. So it doesn't even know the keys.
no,
So that's one way to implement a hash table. Now, usually you do like to know what the keys are and keep them. So typically when you implement this, you would actually store at this location an object that contains both the key and the value. So that's the normal way to do it. But again, in this example that's drawn up here, the buckets only contain the values.
because that one I thought, okay, it's an object has key value.
Objects have key values and they know what their keys are and
Yeah.
everything. So the way they do that in JavaScript does a hash table like this. It hashes Lisa Smith, it gets a 1, and it doesn't write the phone number right here. Instead, it writes an object that has 2 fields, key, value. The key is going to be Lisa Smith, value is going to be the phone number. Okay. But it's it's the same thing. So that way you could run through all of the buckets here and find all of the keys by looking at each one of the objects and looking at the key. That answer your question a little bit more, Rakaya?
Yeah. I'm
Okay.
still confused just about the fact that what if like the buckets list is completely full?
That's another problem.
Yeah, that is what I'm thinking, that if it's already full, like if every index has something
Yeah,
and we want to add more key value pairs.
yeah. So there are several problems with hash tables, which is why we don't use them ubiquitously everywhere. But and then we have to write code in order to deal with these problems. One of them is I can hash 2 names and get the same index. Then I go, what do I do? So what you usually do is you would, in here, like I say, you have an object that has the key and the value. So here I would have John Smith as the key and the value is 1, 2, 3, 4. And then I would, if Lisa Smith also hashed into this index, then I would create then I'd make this an array. And I'd add another element in here. So instead of this holding an object, it would hold an array of objects. And the second element would be John Smith, Lisa Smith is the key, 8976 is the value. So you get an array of all of the values there. And that's how you deal with these collisions. And then if it fills up, then you're just going to start getting lots and lots of collisions. And so these are all going to have lots of values in them. And if you do that, then the hash table becomes inefficient, because if I look up Lisa Smith, now instead of going here and finding Lisa Smith right there, I'm going to find an array. It might have 5 or 10 items in it, and I have to go look at each one. So it becomes less efficient.
Okay, yeah, got it.
So what they do then is deciding how big to make your hash table bucket is a big deal, because you kind of have to have a guess of how many items you're going to have in your table, how spread out are the keys going to be, and things like that. And then they also have algorithms that says if if the bucket list starts getting too full, then let's figure out how to make it bigger and so on. And then all the keys change, so you have to move things around. Not the keys change, the indexes all change, so you have to shuffle things around and so on. But it's a bit of a nuisance. People make a career out of writing efficient hash tables, but they have to worry about all those issues.
Okay, got it.
All right.
Mhm.
So I don't want to get too deep into that because it gets kind of hairy, but those are the issues with the hash table is your buckets can fill up and you can have two keys that hash to the same thing. So there's actually a bit of an industry in how to write good hash functions. So given John Smith and Lisa Smith, is there something you can do to make it very unlikely that they'll hash to the same value? You know, so there's lots of different ways, things you have to worry about when you're building a hash table, how to make it efficient. So,
Okay.
all right. So those are kind of details about it. The main thing to keep in mind about a hash table, just from a very simple standpoint, the hash table has two pieces. It has the hash function and it has the bucket list. In order to find a value for a key, you hash the key, it gives you the index, you go look at that, go to that index and just retrieve the value. And you know, that's the model you should have in your mind as to how a hash table works. And then let the implementers worry about all the details. All the components. Okay.
Yeah, got it.
So again, to look up, all you're doing is hashing, getting the index, looking at the value right there. If you look up Robert and Robert's not in there, it'll hash to say index 3, it'll be empty. So you'll know that Robert's not in the table. Okay. So then to insert, we did insert, you just like Robert hashes 3, you just write Robert's phone number right there. So that's constant time as well, the insert. Now let's do remove. Update. So Noah, how would you do an update? Suppose I wanted to change Sandra's phone number.
So we send the key to hash function. The hash function look up the key, look up the value.
No,
for
the hash function returns the index.
hash function returns
The hash function returns the index. That's all the hash function does. Key goes in, index comes out. Okay. So it'll return the index, which is 14. Now, how do I change the phone number for Sandra?
Just updating it.
Yeah, just write the new value right there.
That's a new one, like
Yeah.
an object.
So the complexity of this is,
Old one.
yeah, this is again constant time because I'm just doing the hash table and the lookup in the table in the bucket list is constant time and the write is constant time. So that whole operation is constant time. So then, Rakai, how do I remove something, a key from a key value from the table?
So yeah, we follow the same steps basically. We take the key, we pass it to the hash function, we get the index, and then we just remove the value, delete the value from there.
Right, just change that to undefined or null or something. Okay, so that indicates it's not there. So again, that one is also constant time. So all of the operations, look up, add, remove, and update are all constant time, which makes a hash table a phenomenal data structure, which is why it gets used so much. So then since it's so awesome and everything is constant time, why don't we use it for everything?
Because it's not stable, there's no order.
If there's no order. That's one. So if you need to have your data in order, like for a dictionary, it's not a good structure. That's one reason. Any others you can think of?
It's limited, so like you said, we can't grow it in size.
Yeah, can't grow it easily.
Use too much memory.
It uses a lot more memory than just putting everything in an array. And the last one, well, there's lots more. There are other reasons. I just don't know if there are lots more, but there are other reasons. But another big one is, what if you're working with data that doesn't have key value pairs? For example, I just have a list of phone numbers and they're not associated with anybody. Okay. Or I just have a list of words. Maybe they're words in a document. I want to just list all the words in a document. Putting each word in a hash table doesn't make sense because there's no key associated with it. Okay, so hash tables are good if you have key value pairs. So let's go through these. Lists are good for storing collections of data. They're nice, they're great. They have performance implications, so they don't get used for everything. Binary search trees are used primarily if you have if you want your data to be sorted or ordered. And hash tables are great if you
there are key value pairs.
have key value pairs. So that's the main things to get out of all of these three exercises is those three things. Usually what I will do is I'll say, can I solve this with a list? Because it's the simplest one to work with, simplest one to think about. And so I just, if I can solve it with a list, I'll do that. And so you'll see a lot of things that we do in our React code is we have arrays. A lot of our state is an array, especially if it's data that comes from an API or from a database. It's just an array of stuff. Simple, easy to do. Then I'll say, oh, okay, I can't do that because it has to be sorted. Then I'll go to a binary search tree. Or, oh, I have key value pairs. Then I'll go to a hash table. Okay. All right. Good. Let me do the implementation for you. All right. I'm going to build the index. Now, again, to go through what I'm doing for building the index, I'm trying to do, I'm given a bunch of documents that have a title and contents. And I'm trying to go through the content, all the contents, and I'm making an index. So my index that I'm getting is I'm going to take in each word and I'm making each word the key in my hash table. And the value is going to be an array of documents that word appears in. Okay. And I'm going to use a map to do this.
You said you could just repeat that. You said you took each word in the contents.
Each word in the documents, each word in the contents gets added as a key in the hash table. And the value of the hash table is a list of all of the documents that word appears in. Okay. So I have to figure out how to write that code. Let's see. Fortunately, I have the instructor solution that I wrote a while ago in case I forget what I'm doing. Okay, so I'm going to have my index be const index equals a new map, and I'm going to make it a map, this thing right here. All right, so there's my map. And then I'm going to return it. All right, good. So now I have to figure out how to populate it. So I've got a list of documents here. So clearly I need to loop through all the documents, right? And then for each document has content, which is going to be a list of words. So now I have to extract all the words out of the content. And then I'm going to loop through all the words and I'm going to add them to the index.
It's a nested loop.
Okay. Yeah, it's going to be a nested loop, which says quadratic, right? Yeah. So building the index is not fast. All right. So first of all, I'm going to use for each because that's what I'm most comfortable with. So I'm going to loop through all of the documents. So I'm going to for each, and for each of these, I'm going to get a document. So I'm looping through all the documents, and each one is going to be a doc. I'm going to name doc. So now what did I say? Now that I've done that, I have to extract all the words. So let's see, const words equals. And what we did is we do a, I gave you some hints on this, right? How to get them out. Yes, string.match. String.match then returns, whoops, not string, doc dot content dot match returns a list of all of the words that are in that content. This is a regular expression. So that's one of those magic things. And just to kind of go through the regular expression so you understand it a little bit. So in JavaScript, you create a regular expression by surrounding it in forward slashes. So that says this is a regular expression. \B says match any blank space. Okay. So I'm going to match any blank space, 0 or more blank space characters. So if it has a space or space or stuff like that, then \W means match a word letter, a word character. So word characters would be upper and lowercase letters. Okay. So this \W matches all word characters, and the plus means match one or more. So it's trying to match all of the word characters, and then I'm going to do backslash space. So what it's doing is it's saying find a space, find all the letters, and then find another space. And whatever is between the two spaces, that's what is in this parentheses right here. Okay. So that's what matches. This is how it matches all the words. And then the G means do it globally, which means usually when you do a match with a regular expression, it stops as soon as it finds one match. But we want it to find all matches. So the G says do it again and again and again until you found everything in the document. So this will split that content up into all of the words in the document and return them as an array. So words will be an array of strings, an array of words. You see, it's const. Oh, well, okay, that's a kind of a tough type. But anyway, that is an array of strings, basically. Okay. All right. So now I've got my words. It's an array of strings. There is one thing I really should do, though. Whenever you work with text and you're doing matching and things like this, you almost always want to convert everything to lowercase. So let's convert it to lowercase first. Before I do this, to locale lowercase, and then do the match. Okay, so now my words contains all of the words in the document. This words is an array that contains all the words in the document. And now I want to loop through those and add each one of them to my index. So now I'm going to do words.for each.
Would it have been different if we would have done the to locale lowercase after the match method?
At the end here? No, I don't think that will work because match returns an array. An array doesn't have a to lowercase method. You can't convert an array to lowercase. You can only convert a string to lowercase.
Okay.
Okay. But you could do the conversion to lowercase down inside of here. You could say w.to lowercase. That would work. And it mostly works if you don't even bother with this, except for then if they say fish with an uppercase and fish with the lowercase, it'll go into your index as 2 different words. So usually to avoid that, you just convert everything to lowercase. Okay.
Okay, got it.
All right. So now what do I want to do? I want to add this into my map. I want W to be the key. And I want a set of documents that it shows up in to be the value. So the first thing I need to do, I could just add the word to I could just say index dot set, and I pass it the key, which is the word, and the value, which is going to be a new set of documents. Okay, I could do that. But then if I see the same word twice, the second word will clobber the first one. So what I need to say, do I already have this word in the index? If so, then I need to add the document to its list. And if I don't, then I do this so I can put it in for the first time. This is a very common pattern that you do when you're processing data. You'll have something like a map or an object or a set or something of things, and you'll say, I'm accumulating all of something. And so first of all, I check, is it already there? If not, create a new one. If it is already there, then I push into it. So basically, if it's already there, I want to push the new document into here. And if it's not there, then I want to start brand new. So before I can do this, by the way, it'd be interesting to see if I just save, let me npm test. I'm really curious how bad it is with this code. Received. I expected all of this green stuff, and I got an empty set. That wasn't very good. So, oh, whoops, that's the query. Sorry, looking in the wrong place. Query. Where's the build index? Yeah, map index. That's this one. I expected to get about and cook and effectively and fish and all that stuff. And instead, what I got was I got several words. That's hard to see, isn't it? Let me pop it out. I expected to get, for each of these words, I expected for a while to show up with two documents. This one named naps and this one named dinner. I expected that the word while is in both naps and dinner in this test. So that's what I expected. What I got is I got while just as an empty set. Okay, so that wasn't quite right. So I need to, it didn't quite work. So let's refine it. First of all, I don't want an empty set. I want the document. So let's put the doc in it. What? Oh, it needs to be a new.
Yeah, that would say.
I'm sorry, I'm gonna, instead of wasting our time, I'm gonna look at the solution. How do I do this? Oh, I have to put it in an array. That's ugly. That's a yucky thing about JavaScript's API. Okay, anyway, so I'm gonna create a new set. I'm gonna map that word to a new set that has that document in it. So let's look and see what it did for me. So here is what I wanted. For example, while at the bottom, I wanted while to have two objects in it, two documents in it, naps and dinner. Instead, what I got was, what I got was, the first one, this is kind of hard to read, but what this is telling me is that I was expecting to see the naps document in here, and it wasn't there. That's why it's green. I expected it wasn't there. This one that's gray, I expected it was there. So dinner was there, but naps wasn't. And that's because when I first inserted naps, and then I came along and I got dinner, and dinner got inserted in, and it clobbered the previous one. So I don't want to clobber the previous one. I want to add it to it. So in order to do that, I have to first check and see, is this word already in the index? So you check to see if it's in there. You say, let's get the current value. Let's see, set const index in docs. The index docs equals index. I'm looking in the index to see if the word's already in there. So I do a get. So in docs retrieves the current value of the current value for the key W. It looks in this index right here that I'm building. It says, is W already in there? If return it. If so, return it. If not, it's going to return undefined.
So get it returns index, right?
No, it returns the value. Get returns the value. Remember, the value is going to be a set. The value is a set. So it's going to either be a set of everything that's in there or undefined. Okay, so if it's not there, if there's no W there, sorry, if there's no in docs, then I want to put it in like that. Okay, but if it is there, then I want to add it. So I want to, I have to say in docs dot add the doc. Okay, so what this code does is it says, let's look and see if this word's already in the index. If it's not, let's add it to the index like this. If it is, let's add it instead to the documents that are already there. So it's got a list of documents, and I want to add the document to that list. So if the word's already in the index, get the documents that are currently there, add the current one to it. If it's not there, then just set it to this document. So this is the add code. This is the update code. I'm updating the document by adding to the document. I think that's going to work. Let's save it and see. Run. Map index. The tests all pass. So that's it. It was so easy. Why did you guys fretting over this so much? Sorry. It's not easy. It takes a lot of thought and a lot of thinking about exactly what's going on. And so I tried to give you enough hints that you can figure it out. Maybe you did. I don't know how far you guys got, but this is the way you do it.
Could you?
So I'm going to walk through the code one
Okay.
more time. First of all, I create my output. This is what I'm going to return, which is a map, which is a hash table. This is a hash table where the key is a string, which will be a word, and the value is a set of documents, which is a list of all the documents. The thing that makes a set different from an array is a set guarantees that they're all unique. So if I have an array and I push the same thing in twice in an array, then it just get another one, just grows. With a set, if I try to push the same document in twice, it ignores the second one. It just makes sure there's only one of each kind. That's how set differs from an array. It just only has everything in it is unique.
So the index is actually an object containing a key value.
The index is a map, which is a hash table with a bunch of key value pairs in it. So the keys are the words and the values are the set of documents that word appears in. All right. So then I'm going to loop through each document. And for each document, I'm going to get all the words out of it. And once I've got the words, I'm going to loop through all the words. And for each word, I'm going to ask the question, is that word already in the index? If the answer is yes, then I'm going to add my document to the list of documents for that word. If the answer is no, I'm just going to add the word to the index with a set that only has one item in it. The current document. Okay. Are we okay on that?
Yeah, you made it look so easy.
Yeah, I made it so.
Got lost in the hints that were given, because out here it said if the word is not present, create a new set and add a current document to it. Then add the word and document set to the document index. And you've all done it in one line. And you're all struggling with like 4 or 5 lines of code.
Yeah, you can do this in 4 or 5 lines of code too.
But it was getting confusing. What you've done is so much simpler. So
So what I said was do it in several steps.
yeah. So it was,
Word docs.
hmm.
Close. This. Okay, so now I create the set which has that document in it, and then I set the index. I add the word to the hash table with the value being that set of documents. Okay, so yeah, it's hard to describe how to do it. It seemed to me like it was more logical to describe it as multiple steps, and then and then you can combine it down into one line of code if you
Yeah.
wish.
But
Doesn't
even the terminology is confusing because here it says add, but what add is actually doing is updating. It's
Yes.
not. So yeah, that way it does get a little confusing.
Yes, yes, that's true. You're calling set, but what you're doing is you're adding that word to the index by calling set. That, I guess that's confusing. Maybe I should change that phrase.
Well, okay, can I ask you this question regarding the if else, line 19 to line 24? So what is happening? So,
I'm checking here to see, was that word in the index? If this returned undefined, then the word was not in the index. Okay. So index.get says, tell me the value for this word. And if the word's not in the index, then return undefined. So I check. If it's not there, then I have to add that word to the document. I have to add that word to the index. And you add it using index.set.
to the index document.
Yes, I'm adding it to the index hash table. The index is not a document. The index is a hash table, or in our case, a map. Okay, the index is a map or a hash table, two words for the same thing. Okay, so if the word is not in the index, then I add it to the index using dot set. Okay, and then if it is in the index already, then indocs is going to be a list of all of the documents for that word. And so I just need to add my current document to that set of documents. Maybe I should call it W docs for Word docs. The words, the docs that the word is in. Okay.
Yeah, the naming is.
Okay. I set it for index docs, but it's really the word. It's the documents for the given word. These are the documents that are corresponding to that word. Okay. All right. All right, let's go on to do the second part. I only have 15 minutes, so I need to go kind of quick. Let's do the second part. I'm doing the search. So for the search, I'm going to be passed a search query. And I have to take that query, break it down into words. And then for each word, I need to look up that word in the index. And then get the documents that word is in and add it to my output. So it's actually kind of simple. So this part is, I think, conceptually simpler. So let's go look at the code. I'm going to create my docs. So I'm putting a list of documents that this index is, or sorry, that this word that contain this word, and it's going to look like this new set of document, like that. So there we go. I start out with an empty set, and I'm going to return it. All right. So now I need to break my query into words. And we know how to do that. We just go and grab this code here. Words. I like to call these terms, they're search terms. And I'm searching the query. And I'm going to convert it to lowercase, so I'm always doing lowercase matching. So that gives me a list of all of the words in the search term, in the search query. So terms is all of the terms, all the words in the search query. Okay. So now I need to loop through that. So terms dot for each, I'm going to search through it. And I'm going to get a word out. I'll just call it term. And then all I do is I look up in the index to see if that term is in there. So let's get all of the documents. T-docs this time equals index dot get the term. So I'm now looking up that word that was in the search term. I'm looking up that search term in the index and getting all the documents that that word appears in. And that gets assigned to here. Okay. It's possible that word is not in there, so I have to be careful of that. And then I need to figure out, then I need to go and I need to get all of these documents in T-docs and add them into this set. Now, unfortunately, this is a bit of a confusing piece of code. I've actually had students intuitively figure it out, but I never remember. So I'm going to look, it's this code right here. So what you do is the question mark you put on there because T-docs might be undefined in case the word's not in the dictionary or not in the index. If the word's not in the index, this will be undefined. So I have to guard against that. But if it is in there, I'm going to loop through each one of the documents that was returned. And for each one, I'm going to add it to this set up here. That's all I need to do. Now I'm done. And all the tests pass. Okay. Any questions? How much of this is just completely transparent and or opaque and ununderstandable?
Yeah.
All right, so let me go through it again. First, I'm creating my output variable. This is what I want to return. And it's going to be a new set of documents. And then I'm going to return it down here. Now, first thing I do is I take the query, convert it to lowercase, and get out all the words that are in it. So now this terms variable contains a list of all of the words that are in the search query. So I'm going to loop through them. I'm going to loop through each one of them, making sure that I don't crash if there aren't any. So I loop through, and for each word, maybe I should call that words and terms. Will that be more clear? I keep saying words. Let me do that. Sorry. Words. And oops. Word. Okay, that might be a little more clear. Okay, so I'm going to break my search query into words. And then I'm going to loop through the words that are in the search query. And for each one, I'm going to look it up in the index. That'll tell me all of the documents that word appears in. So then I just loop through each one of the documents that appears in and add it to my output. That's it. Okay. Questions?
No problem. I'm gonna watch the video one more time.
Okay. I'll walk through one more time just to make sure it's clear. Oh, I create my output variable, which is a set of documents. I break the query down into words. So this is an array of words that are in the query. Then I loop through all the words in the query. And for each one, I look up in the index. I look that word up in the index and I get all of the documents that word appears in. And then I just go through each one of the documents that word appears in and I add them to my output. Then I'm done. That's it.
So just clarify one more time. So line 11, when you said get the word from the index. So the index inside the hash table.
This index is my hash table and it has key. The key is a word and the value is a set of documents that word appears in. Okay, so there we go. I do a get and I pass it. This index.get says, give me the value of the word key. So it looks up the word key and it returns all the documents that word
So
appears in.
let's search the whole hash table for this, right? Like each one's gonna look.
It's gonna, for every word in the query, I'm gonna look up that word in the index.
On some, okay, so first we search the hash table, then in each index, we're gonna search for the word. So it's like a,
For each word in the query, I'm gonna look up that word in the index. If it's there, I'm gonna get the documents that word appears in. And then I go through and I just add each one of those documents to my response. Okay,
yeah, both because the word for each.
it's just a loop.
So both of these exercises were actually a hash table inside another hash table. Because a get is all, I mean, sorry, map is a hash table and a set is also a hash table, right?
Yes. A set is a special type of hash table. It's actually a table that has keys and no values.
Hmm.
So the purpose of the set, you could do this just using an array, but then you'd end up with the same document in there multiple times.
Right, got it.
Yes,
Okay.
so a set just make sure that the value only appears once in the list. You can
Okay.
think of a set as a list where every value in it is unique. You never get duplicates.
Okay. Okay.
So if you wanted to implement this with an array instead of a set, then you would get your array, and then every time you wanted to add a new thing to it, you'd scan through the list. And if you found one that was already there, you'd ignore it. If it wasn't there, you'd push it.
Okay.
Okay. All right. Let me finish up with just a quick discussion about the part we didn't do, which is ranking, because I think it's fun. So when Google was first invented, the two founders, Sergey Brin and Larry Page, were students, computer science students at Stanford. And Larry had this brilliant idea about, sorry, let me back up a little bit. The internet had just come out. It was becoming really big and lots of stuff there. It was obvious that it was very hard to find stuff in it. And so companies came up, Yahoo was the first one that said, we're going to build a giant index of all of the pages on the internet. And you type in a search query, we're going to return all the documents. They built their index by hiring a whole bunch of people who would go out and scan every document on the internet and type in the words and the documents. So this index that we just built, they built by hand. Okay. And then they may have built the index automatically, but then they had humans look at it and say, for this query, I want to return these documents. For this query, I want to return those documents. For this query, I want to return those documents. And so that's how it worked. You type in a query. If one of their humans had anticipated that query, it could then look and see what the documents it should return. It would give those to you. So the problem is that you were relying on the human to take the time to actually go and figure out which document should be returned for which query. You would hope that they got your query in their list, and then a whole bunch of new documents would be added, and the query results would all change, and the humans would have to go back and do it all over again. So it was extraordinarily manual, couldn't be done quickly, and the results weren't very good because they were missing too many things. The queries weren't quite matching what you wanted, and you were relying on whoever was building the results thing. You were relying on their judgment as to what was the most important page. And so Larry Page had this brilliant idea. He said, look, I can tell if a document is important because other pages will have links to it. So if I have a page, say LearningFuze.com, and there are all kinds of pages out on the internet that have links pointing into LearningFuze.com, then that document's pretty important. If I have a document, say Robert.com, nobody knows about it. Nobody has links to it. So it doesn't matter. Nobody cares. Don't want to return that one in the search results. So you only want to return the ones in search results that are important, that other people have the other documents linked to. So it's this kind of backwards pointing. So they take every document, they figure out how many other pages point to it. And then the more that point to it, the higher its ranking it gets. So he invented this. He called it the page rank. And it's actually named, page is not actually a page, an internet page or a book page. It's actually Larry Page's last name. So this ranking is named after him. And so he invented that. And he and Sergey got together and they said, let's build this. And they tried to build it. And they didn't have enough computers to build it. So they went running around campus, all of the computer science offices, and they said, oh, I see you have a computer under your desk that you're not using. You mind if we take that? And they said, oh, sure, take it. So they gathered up all these and until they finally had 15 or 20 computers. And they programmed all those computers to go out and do all of this computation for creating the page rank. And then they were able to do what we just did, with the indexing and the query matching, and then they took all the results and they ordered them by which ones had the highest page rank. And lo and behold, it worked. It gave much, much better answers to all the questions that were, to the queries that were being asked than what were being done by the humans who couldn't keep up with the traffic and the demand. And so they then said, oh, this is cool. It gives better results. Let's go build a company and make $1 zillion. So that's what they did. They built Google and they implemented this algorithm on their computers and they implemented that ranking system. And they lived with that for quite a few years and it worked very, very well. And then as they got more and more traffic and more money, they hired more and more smart engineers. They realized that there were a bunch of other things they could look at besides just the page rank. So, so here are some of the things that they look for. They right now today, they probably have 50 or 100 different criteria they use when trying to decide which 10 out of the million that they got back that they should display on the page. So it's very sophisticated right now, their algorithm. But these are the main ones that they would use. For example, the number of words in the search query that are also in the document. So if I have a page, so I have a query that has 4 words in it. This page matches 2 of the words, and this page matches all 4 of the words. That second one is more likely to be relevant to you. So that moves up in the rankings. And then, so the prominence of the words that match the search query, they also look at. And by prominence, I mean, maybe it's in the page title, maybe it's in a header, maybe it's been bolded or italicized, things like that. So they just look and see how prominent are those words or how many times does that word appear in the document. And the more of those are, then it gets higher, it gets higher ranking. And then they do the page rank, which is what I talked to you about. And then they also will look at, if you log in to Google, they will look at your prior search history and they'll look at your demographic, your interests, and anything else they can figure out about you. And they'll use that in order to trim it down. So for example, when I go out and I search, I'm more likely to see computer software results in my list of results than my wife. When she searches, she doesn't see any of the computer software results because of this last bullet point. They're checking my search here history and my demographic and information they know about me, and they're using that to rank all of the results. So they take all of these factors into account. They assign various weights to them, and then they calculate a score for every document. And the 10 or 20 with the highest score are the ones that get displayed to you. Okay. Kind of cool. That's Google. Now you can go build your own Google.
Very cool, yeah.
All right. So that's all I want to say on this exercise. Are there any other questions at all on this?
Just one last question. So the index mean the hash table.
The index is the hash table.
Because
Yes.
naming.
Okay, the index is the hash table. It's called the index because it is an It's like the index in the back of a book. It's exactly what it is. In fact, it's almost 100% an index in the back of the book. It lists all the words, and for every word, it tells you which pages that word appears on. The search index it lists all the words, and instead of page numbers, it's URLs.
Oh, the last page of the books. I'm gonna go.
Okay, yep, go. Oh, you guys that don't even know what books are anymore, get a technical book and look in the index. Okay, yeah, the ones on my shelf back there. Okay. All right, so that's how that all works. Tomorrow, we're gonna jump into databases and get going on more practical stuff for your back-end journey. All right? Questions? Done? Cool. All right, we'll see you in the morning. Let's start right at 9 o'clock because there's no Q&A or anything. We can jump right into databases.
You won't be coming in late tomorrow? It's Thursday.
Oh, dang it. Thank you for reminding me of that. I will be. I'm going to release, thank you. I'm going to release 2 exercises right now, and you work on those till I get in. I won't get in till, again, normally like 10:30 because my wife has physical therapy. Okay?
Okay.
All right.
I hope she's gonna be okay, for sure.
She's doing really well now. Thanks.